Hi guys, chapter 14, multiple integration. In the first section, we're just going to see what iterated integrals are, and we're going to look at finding areas in the plane using iterated integrals. So as an introduction problem, if we know that the first partial derivative f sub x of xy is 2xy, then what is the original function? And we can integrate 2xy, that's not hard, it's x squared y, but be careful, instead of having a plus c, realize that any function f that has a term that is only in terms of y, like sine of y, or e to the power of y squared minus 2y plus 7, would also qualify as being an extra term. It's not just constant. Any function of y, which we write c of y to give this, to point out to the fact that that looks like a constant. It's a constant in terms of x, but not in terms of y, is also possible. So as a refresher, here's an integral, the integral from 1 to x of 2x squared times y to the negative 2 plus 2y dy. So we are integrating in terms of y, and it is okay in the limits of the integral to have another variable here, x. So the integral is negative 2x squared over y plus y squared, integrating it from 1 to x. So we substitute x and we subtract, substituting 1, and we get 3x squared minus 2x minus 1. So an iterated integral is a series of integrals that are performed consecutively. Here's the first example. We have an integral here which you have to connect like this. So this means that y goes from 1 to x, and then x goes from 1 to 2. So it is as if there were big parentheses right here and there. We never put these parentheses, but this is how you can visualize it. So first we're going to treat the integral that is inside. It's an integral in terms of y because it's dy, and that is x squared y minus 2x y squared, which we evaluate from 1 to x. And so every y is substituted with x, which explains why x squared y becomes x cubed here, minus 2x cubed again, because x times x squared will be x cubed, minus y equals 1 here. So we simplify, and now we are back to a simple integral in terms of x, and the last steps are pretty straightforward, and the final answer is negative 37 over 12. If we have a single integral, we always integrate on an interval from a to b. When we have a double integral, like in the example before, we are actually integrating over a region. The region of integration R is the region determined by the intervals defined by the limits of integration. Note: the inside limits of integration can contain the outer variable, but the outer limits must be constant with respect to all variables of integration. Looking at the example down here, the outer variable is x. So in my inside integral here, the integral from 1 to x, it's totally fine to have an x, because when I integrate in terms of y, then x will be part of the integrand that I'm integrating in my second step. However, I could not, instead of the 1 and 2 here, the limit, I could not have a y there. I could not have an x either. Of course, like in AP Calc AB, you can't integrate something in terms of x and then have x as part of the limits of the integrals. But in the inside integrals, you can have the outer variables. Here's the opposite example. The inside integral is in terms of x, so it is okay to have y squared, but it would not be okay to have x out in the outer integral. Therefore, given a region graphically, in order to establish the limits of integration, we must pay careful attention to the order of the variables. Sometimes there is only one possibility. So in the two examples here, this one has two possibilities, this one has only one. Let's look at that first. If we want to integrate over the blue region here, so that is how we're going to define the limits of our two integrals. And imagine first that we know function g1 starting here and going all the way here. So it's y equals g1 of x. And then we also know a function g2 of x that goes over the upper part of the region. Then we can say that the integral is the integral. In terms of x, we are going from a to b, because this is the beginning of the region, and here is the end of the region. So for the integral in terms of x, we are going from a to b. And then for one of these values, x, we are going to go from here to there. So for the integral in terms of y, we are going from g1 of x to g2 of x. And this is why the limits of the inside integral are g1 of x and g2 of x. We can also integrate first in terms of x, which is what I did here. So let's focus on the outer integral first. Y will go from here to there. So we are going to integrate from c to d. And this time we can't use g1 and g2 as functions because they would not be functions of y. If you do what we typically call the vertical line test, would now be a horizontal line test, we would see that it cannot be a function of y. So hopefully we know two functions, h1 and h2, which go from h1 would start here and go up there, while h2 would start here and maybe it's a semicircle ending here. In that case, we can say, again for the outer variable, we've figured this out, we are starting at c and ending at d, and then for some value y in that range, we are starting here and integrating all the way there. So we are integrating from h1 to h2 of y. So that is the difficult thing, I think, in today's lesson. In this example here, we can see that it's not going to work in two ways because of kind of this thing that curves in again. We are only going to be able, if we want to express it as one double integral, we are going to have to say, okay, I'm going to integrate x from a to b, which explains the a to b here, and then for a selected value, let's pick it here, I am integrating from g1 of x to g2 of x. It doesn't work if you try to flip the order. If we try to write an integral similar to this one here, where the outer integral is in terms of y and we integrate from c to d, so we would integrate from c to d, and then picking a certain value, you see how we would really be in trouble here and there. It would not allow us to write a single double integral and get and describe the region. So sometimes there is only one possibility. It would still be possible to integrate in the order dx dy, but we would need to split the region into many separated regions. Maybe we would have to split the region here and then treat it as two separate regions. Alright, so if we are given limits of integration, it is absolutely key to be able to sketch the region that it corresponds to, and vice versa. If you have a region that is given geometrically, it is absolutely key to be able to describe the limits of integrations that correspond to that region. So here we have x ranging from 1 to 2, and then we have y ranging from 1 to x. So let's start with the outer variable. I think for me it's the easiest. Maybe other people think differently, but for me it's easier to think of the outside first. X ranges from 1 to 2. So x goes from 1 to 2. And I draw the vertical lines to show the limits. I'm going to go from 1 to 2. And then y ranges from y equals 1 to y equals x. It's better to say, I could have done the same earlier. It goes from x equals 1 to x equals 2, and here it goes from y equals 1 to y equals x. So we need to sketch these two graphs, y equals 1 and y equals x. And now for any of the values between 1 and 2 for x, I'm going from y equals 1 to y equals x. And it defines that triangle. Next example, this time y is the outer variable of integration, so it goes from y equals 0 to y equals 2. So I'm sketching these two lines, y equals 0 and y equals 2. And then for a certain value in that range from y equals 0 to y equals 2, x ranges from x equals y squared to x equals 4. So I need to sketch x equals y squared. I need to sketch x equals 4, and I start at x equals y squared, and I go until x equals 4. And if you do that for all of the values of y between 0 and 2, you can see the region that is described. Area of a region in the plane. So if we are looking for the area of region R here between two functions g1 and g2, we know how to do that in AP Calc AB. In multivariable, we are taking one step back, and we are saying the area of this region here is the integral from a to b of the integral from g1 of x to g2 of x of dy dx. When there's nothing here, it means there's a 1, right? It's 1 times dy dx. You can also flip it and solve it like that and write it like that. Of course, it depends on the situation. So we know from AP Calculus AB that the area of a region, as shown just previously, is the integral from a to b of g2 of x minus g1 of x dx. It's the top function minus the bottom function. But we can take a step back from that and use the fact that actually g2 of x minus g1 of x can be written as the integral from g1 of x to g2 of x of dy. This is 1 times dy, so if you integrate, you can easily see that you get this. And therefore, rather than writing g2 of x minus g1 of x, you can write the integral. And this is maybe a purer form. It's also a form that can be better expanded to 3 dimensions, 4 dimensions, 5 dimensions. It's just a sequence of integrals, and then you have dy dx or dz dy dx if we're looking for a volume, etc. But it's really immediate to see how this goes to what we know from AP Calc AB. In this little example here, we will see how that happens. Find the area of the region bounded by the two graphs f of x equals sine x and g of x equals cosine x. Here's the sketch. The boundaries are not even necessary. We had been able to describe that it's the region strictly bounded by the two functions. Of course, there's more regions like that, so maybe this is why we have limits of integration, so we are not confusing the region with the next region that comes up. So using multivariables description of an area, we write this, and then in our first step, the integral of 1 dy, we reach what we would have started with in AP Calc AB. So from here, it's a straightforward problem because this is what we would do early in the year, really, in AP Calculus AB. Well, early in the chapters of integrals. And so I'm not going to go through the details of how to solve that. The area is 2 root 2. So we are in multivariable again. We are just going one step backwards from where we used to work in AP Calc AB. Now, final example. Find the area of the region bounded by x equals 0, x equals y squared minus y plus 1, y equals 0, and y equals 2. It is not the final example, I'm sorry. So here the exercise is to be able to determine what the region of integration is. So x goes from 0 to x equals y squared minus y plus 1. Maybe let's focus on the easier part here. Y goes from 0 to 2. So we're going to use that as the outer integral. Y goes from 0 to 2. And then that means the inner integral can have y in its limits. We are integrating y from 0 to the function x equals y squared minus y plus 1. So these are the graphs, like y equals 0, y equals 2, that's easy, and then x equals 0, x equals y squared minus y plus 1, which has the maximum here. It goes down to y equals 3/4, I think. And so the region is this one here. From there we integrate, the inner integral is super easy, and then the outer integral is just as easy again. So the integral is 8/3. This corresponds to what we did in AP Calc AB when we were integrating in terms of y. Okay, this is the final example. This one is interesting because it shows that sometimes you have to switch the order of integration in order to integrate. It is a well-known fact that the integral of e to the power of x squared is not possible algebraically. And if you are taking stats or AP stats, you may know the bell curve, and that is similar to e to the power of x squared, and you cannot integrate it by hand, and that's why a few decades ago there were just tables and tables of values, and nowadays we just use our calculators to find areas under the bell curve. So this is an example. For e to the y squared dy, you're not going to be able to integrate that. There's just no solution. It's not that we don't know how to do it. We know that it is not possible to integrate algebraically. We can do it numerically by successive approximations and with a calculator, with a computer, but not algebraically. So in order to be able to find this integral, an idea is to switch the order of integration, and maybe we are lucky and it is possible to integrate dx dy rather than dy dx. To do that, we are basically doing the two steps that we've seen earlier. We want to sketch this region of integration and then use the sketch that we've done to redefine the double integral in the other order. Okay, so here x goes from 0 to 1, x goes from 0 to 1, and then y goes from 2x to 2. So y equals 2x, y equals 2, and it yields this triangle here. Now that I've done that, I can try and define a new integral where I'm going to focus on y first. So y goes from 0 to 2, and then for any y in the range from 0 to 2, if I pick a certain one, x will go from 0 to hitting the line y equals 2x, which is the line x equals 1/2 y. So we are able to rewrite this this integral. We integrate from 0 to 2, and then we integrate from 0 to x equals 1/2 y of 4e to the y squared. This doesn't change. What changes is that it's now dx dy. Great news. The inner integral here is very easy to integrate since there isn't even an x in it. So the integral is x times 4e to the y squared. If we substitute the limits of the integral, we get 2y times e to the y squared. And now that is okay, because notice how 2y is actually the derivative of y squared. So I can use u substitution. U equals y squared. Therefore, du equals 2y times dy. Might be a little rusty how to do that, but it'll come back very quickly. And therefore, it's the integral of e to the u du. Pay attention to the limits of integration. Y equals 0, y equals 2. We have to change that because we now have u here. So it's u equals 0 squared, so it stays 0. However, when y was equal to 2, it gives a new limit of integration, u equals 4. So we integrate from 0 to 4. There's two options here. You can, since we have the limits of integration in terms of u, I can substitute immediately and get e to the 4 minus 1. Or you could substitute back here and say, okay, it's e to the power of y squared, and then substitute 2 and 0 again. In either case, you will get e to the 4 minus 1, of course. Okay, thank you for listening to this first section on multiple integration.